let me just do slightly bigger. We'll do a quick overview. So plan for today. So first, the main goal is that matroids are supposed to generalize the abstract of what we know as linearly independent sets, but we're just going to call them abstract independent sets. And we're going to see how that applies in different contexts. So part one, we're going to look at what abstract independent sets. And the idea is to lead with an example for intuition. Then we can move on to like the proper definitions and so on. Once we have the definitions down, then we want to study some nice families of matroids. Another thing is going to come along the way as we're building our characterizations. Then there's this, you can build from the nice families and the characterizations, but I'm going to skip it. So there are constructions, meaning like from some matrices I can build others, and those constructed matrices are really useful in theorems and when you're building other things. But just for brevity, I'm going to mention duals, and everything else we're going to sweep under the rug. So this would include duals, which is the only thing I'm going to cover, but there would be other constructions. So like by deletion, contraction, and other stuff that we're not really going to do. So these are going to be not really covered. I'll briefly mention why I was interested in this in the first place. Interest. And if time allows, we'll go over some uses. So that's the plan for today. Starting with the intuition, there are 3, and then we'll build into 4, but mainly 3 examples. So I'm going to call them example 1, example 2, example 3. They're going to come from different points of view, but they will end up representing more or less the same idea. And that's where the intuition comes in. So for example 1, the most straightforward one is linear independence. So I'm just going to draw my axes for R3. So let's pretend that this is R3. And in R3, I'm going to do colors. I'm going to draw some vectors. So I'm going to have a vector here. I'm going to call it A. Vector here. I'm going to call it B. C. D. If I do another one that's parallel just a little bit longer, we'll call it E. And then over here, the 0 vector will be F. Then for example 2, switch colors. I'm just going to draw this multigraph. So I'm allowing parallel edges, meaning if I have 2 vertices, I'm allowed to connect them with more than 1 edge. And what I'm going to do here is I'm going to label the edges. So I'm going to call this edge A. This one is going to be F, B, C, D, and E. And third example, let me do new color. We'll do purple. I'm going to have a bipartite graph. And I'm going to connect this to labeling 1, 2, 3, A, B, C, D, E, F. Okay, straighter. Okay, there we go. So, common points, all of these pictures have the letters A, B, C, D, E, F. And I want to draw parallels between them. So the task is, can you build independent sets? Now, in the first example, this is more or less clear. I'm looking for sets that are linearly independent. So for example, if I picked A and B, that is a linearly independent set. A and C is linearly independent. However, D and E would not be. And I'm looking for all the possible independent sets I can build. Now, in the case of example 2, what I'm going to call an independent set is a set of edges that does not form cycles. And cycle is exactly as it sounds, just intuitively, I go from one vertex through the edges back to that starting vertex. So for example, if I wanted to travel from this vertex through B, E, and then C, this would form a cycle. This DE would also be a cycle. So I'm looking for subsets of edges that do not form any cycles. And then for example 3, I may need to move this down just a little bit, so I need more room to explain. What I'm going to do is for 1, 2, and 3, I'm going to create sets. So 2, 3. In the context of bipartite graphs, we're going to associate it to either a system of distinct representatives, so SDR, or otherwise a matching. And the classical example is the marriage theorem. So supposing that you have 3 people here and 6 other people there, and these lines indicate who the 3 people would be willing to marry. Because I don't really like the marriage analogy, we can just go with, we have TAs here and possible TA assignments over there. So for example, TA number 1 is very picky and will only do assignment A. TA number 2 is less picky and is willing to do either assignment A, B, or C. TA 3 is more willing to do any of these 5 assignments, but really no one wants to do assignment F. And what we're trying to figure out, so an SDR or a system of distinct representatives, would be which assignments can I actually assign to the TAs. So for example, if I wanted to give assignment A to TA number 3, I'm not going to be able to give anything to TA 1. And I'm basically playing with how many ways I can assign these things. So that's where these sets A1, A2, A3 come in. A1 is the set of assignments that TA1 is willing to do, so that would be just assignment A. TA number 2 is willing to do A, B, or C. TA number 3 is willing to do A, B, C, D, E. And a system of distinct representatives would be something like picking A for TA number 1, maybe B for TA number 2, and D for TA number 3. So ABD would be one possible system of distinct representatives. So I have one assignment for each of my 3As, and those assignments are distinct. So I can't assign A to more than one person. Questions so far? What I'm looking for with these independent sets?
Not yet.
Okay. So, yeah, it should be good enough. Question 1. If I'm looking at the letters A, B, C, D, E, F, which letter is not like the others? And not like the others in the context of trying to build these independent sets. Thoughts, suggestions? The most different letter out of all of them?
F. Can I say F?
Correct. So F is the most unusual out of all of them, and why would that be?
Well, in each example we're in.
Yeah, it's not a rhetorical question. Like,
it's like the zero vector. I don't know. I don't know how to explain. It's a zero vector. It's a cycle, and it's a thing that doesn't have anything going to it.
Correct. So I can't add F to any of my collections. I can't add it to any of the independent sets. Question 2. If I had to pick a second different letter, is special besides F. So besides from F, what other letter seems to be special? So it doesn't drag on, I'm just going to point out it should be A. And what A has that is special is that I can always add it to my collections. So for example, in the linearly independent case, this is completely separate from everything else which lies on this plane. Over here, this is never going to close a loop. And then over here, this is the most accessible task. Anyone is willing to do it. I can always add it to my system of distinct representatives. Be chosen. Then we have motivating question number 3, which pair, I can't spell, pair of edges stands out? Oh, I should probably not say edges, letters, depending on the context. So which pair of letters stands out here?
D&E,
D&E.
I think.
And the reason why, again, intuitively, is that these are basically interchangeable. Meaning, if I'm trying to build an independent set, let's say over in example 1, I can either choose D or E, but not both. And they serve more or less the same function. Same over here, they're parallel edges. So if I'm trying to build a set, I choose either one or the other, but not both. And on the right-hand side, it's a little bit less explicit, but they serve the same function in the sense that only 3 is willing to do them, and they have the same number of edges.
Lina, I have a question.
Answer. What's the question?
So what is your definition of linearly independent or linear independence in the example 3 case? Is it like, for example, ABD would be a linearly independent set?
So I'm going to call a set independent in the 3rd case if it is a system of distinct representatives, or if it's derived from a system of distinct representatives.
Okay.
More questions? I'm about to scroll down. Or actually, let me just write it here while we're different color. Sure, blue. No, also blue.
A question.
Green.
I think
What's
B
the question?
also is interchangeable. B and C.
B and C.
Uh-huh.
And so in this picture, kind of, but they're not truly parallel. And in this picture, also kind of, but they're not exactly parallel. So I'm going to give you a definition for parallel edges or parallel things in a minute.
Okay.
These 3 examples are not exactly the same, but they were built to have the same moving parts so that I can answer these 3 questions the same way.
Okay.
Austin has the chat. He says, to clarify example 3, the edges themselves, like 1A, 2B, 3D is the set, right? So 1 from each set is, I think, what you were saying, yeah?
So in example 3, I'm not looking at the edges as my objects. I'm looking at this collection of like possible tasks for each of the things on the left. And the sets that I'm looking for, the independent sets, will be these systems. So for example, this orange one would be one system, but I could do a different system if I picked A here, C here, E there.
So it'll be a triple of vertices in this case, yeah? One.
Correct. It can be a triple, or I can even, like if I wanted to, it's not ideal, but if I really wanted to, no, different color. I could also choose A here and then C there and leave this person without a job. And that would still be valid.
Yeah, okay.
So far, so good? So if I wanted to list the all of the possible independent sets that actually work the same in all three examples, is here. So independent sets include the empty set is trivially independent. If I pick any single thing, those are all independent. Oh wait, not the last one, sorry. This one cannot be added to anything. So every single thing except for F. F is the exception. Then I can add some of these combinations. So this, I'm going to write A, B as AB, just for simplicity writing. I can have AC, AD, AE, BC, BD, BE, CD, CE, and then out of 3 we can do ABC, ABD, ABE, ACD, ACE. Okay, so those are all the possible independent sets, and then this collection, which I'm going to call script I, is going to be what we focus on. So definition, go for black. A matroid consists of a ground set E, which for all intents and purposes, we're going to assume is finite, but there is such a thing as a theory of infinite matroids. It's just beyond the scope of today. And a collection of subsets of, I'm going to write the power set of E as 2 to the E. So this is power set of E, I, such that, and I'm going to have 3 axioms that I need I to satisfy. So first axiom, I1, we're going to ask the empty set to be included. Second axiom, for any independent set in my collection, and J, a subset of that independent set. This is, hold on, it should look less scripted. The subset, we have that J is also independent. So back to the examples, if I have that, let's say A, B, and C is independent, then any subset of that, just A and B, would also be an independent set. So it's closed under containment. Axiom number 3, and then this one is special, so it has a name. This one is the exchange axiom. And what it says is, if I have any 2 things that are independent sets, and one of them is bigger than the other, then I can find some X, some element that is in J but not in I, such that if I add X to I create another independent set. So assuming that J is a bigger independent set, I can build on I to also make another larger independent set.
Maybe a dumb question. Why is it called the exchange axiom?
Here it's less clear that I'm exchanging something out, but there are equivalents for other axioms that I'm going to mention later. And there you're actually very clearly exchanging one element for another.
Okay.
It's just going to be the same principle of I can basically replace, in the case where J has exactly one more thing than I, you could like replace one thing, and you can replace most things in J with I.
Okay, maybe.
And it would be kind of exchange, yeah. But in when we get to basis, it will be an actual like element for element exchange.
Okay.
So let me just highlight these. And reason why I'm highlighting these is because we're going to see that there's multiple axiom systems that can be used to define a matroid. This is just one of them. So with these properties in mind, we can actually prove proposition. Let's do it in blue and slightly darker. So proposition, and I'm gonna do a 3-for-1. These would all be separate propositions, theorems, but I'm not going to include the proof, and I'm just going to mention them to justify the examples. So the first one, if I have a finite set of vectors in a vector space V, and let script I be the collection of all linearly independent subsets of E, then this MEI is a matroid. And sometimes this might be denoted as just M of E. Oh. In the second case, so for example 2, we can let G be a graph. So I have the vertex set, has an edge set, and I'm going to ask this to be a connected graph. Just to rule out the case where I have a bunch of loose vertices and nothing to connect them with. And I'm also going to consider I the collection of independent sets, but this one is going to be independent in the sense of not forming cycles. Independent edge sets. Then is a matroid. And we can usually write this as matroid of the graph G. And then alternately, we could have in a bipartite graph. So if I have G, I'm going to use this for this joint union. It's just the vertices were separated into two sides. I had them on the left and on the right. I'm going to call them A and B. And here I have to be more careful with the definition. I have A1 through AN subsets of B. So of the right-hand side, I'm going to pick possible assignments that each person on the left is willing to take. And let me script S is collection of distinct systems of distinct representatives. I am going to, maybe I'll need more room. So I'm going to find my dependent sets based on that collection. This is going to be subsets of the things that are in S. Then if I take things on the right, along with that collection of independent sets, this is a matroid. And sometimes this is just denoted by the set on the right. Now I'm going to move these things around a little bit. Let me see. There. Just so I can name them. Because I'm saying that these are matroids, meaning the definition above was the general matroid, but these are specific kinds of matroids. So this one, an example 1, is what we call a linear matroid. This one is what we call a graphic matroid. This one is a transversal matroid. Questions so far?
Not yet.
Not yet? Okay. So the way you prove these things is you actually just check these three axioms. Usually the first one is kind of trivial. Second one doesn't really take more than 30 seconds. And then third one is where you actually have to put in some work. But you prove them all by just checking the three axioms. And I'm going to add it here because it would be relevant. There is a fourth kind of matroid we could be interested in, and I'm going to call it an algebraic matroid. So algebraic matroids use algebraic independence. So just so we're on the same page, we'll do a little parentheses here. I'm going to let F and K be fields, where K is an extension of F. We say that elements T1 through Tn are dependent if there's some polynomial on n variables such that the polynomial applied to these T things, T1 through Tn, is 0. So if there's something relating them, I say that they are algebraically dependent. I guess I should point out this is algebraically dependent. And by extension, they would be algebraically independent if this thing does not exist. So the proposition here would be oh, what is this? Okay. Let F, K, fields as above, where K extends F. I is going to be the collection of algebraically independent sets. Then, oh, wait, I need E subset of K, finite. Okay, there we go. Then this is a matroid. And how am I doing on time? Hold on. Yeah, maybe for time's sake, I'm not going to lay it out, but I have a way, like a system of equations and equivalences between letters A, B, C, D, E, F, to turn this fourth example into something equivalent to these three. So we actually get the same independent sets and they have the same properties. But I have it here as something I can skip. So I'm going to skip it to move on. Maybe from the axiomatic point of view, this looks a little bit like when you define a topology in terms of sets that satisfy certain properties. But just like with topologies, it's not useful to be thinking of it as the entire collection every single time. What you want to do is build a smaller collection like a basis that you can always recover all of the independent sets from. So we're going to do that. Definition. A base of a matroid is a maximal independent set. And then I can have this script be a base here is a basis for the entire thing. So if I wanted to recover I from the things in B, all I have to do is check containment. It would be all of the i's contains in B so that B comes from basis. And as it turns out, I can define basis axioms. So I can have B1, B2. This one says this is not empty. And this one says this one's an actual exchange axiom. If I have two things in my collection and in one but not the other, then there exists some B that is here but not here, so that I can swap them out. Without A, but then adding B, this should be singletons, is in my collection. So let's box these in. This is another axiom set. And now that we have this axiom definition for basis, what is actually a theorem, I'll do it in a slightly darker, so theorem if I were to just give you a ground set with a basis satisfying, yeah, I think that's B1, B2, describes a matroid. So the message here is I can be recovered from this collection with the axioms. And also while we're here, tying back to the notion of basis in linear algebra, any base for the same subspace will always have the same number of elements. So that's also a thing here. We're going to use definition, or actually no, proposition, so that I can justify the definition. Proposition, any two bases of a matroid have the same size, so that I can do definition. The size or the cardinality of a base is the rank. So just like we had an abstract definition of independent sets, we're going to have an abstract definition of what the rank function is, but just hold that thought. This rank, if we compare it in the three main examples in linear, graph, and transversal matrices, in the linear case, the rank is exactly what you're already thinking of. In the graphic case, the rank actually connects to size of spanning trees, where a spanning tree, supposing I had a graph, you connect a couple more things. There. A spanning tree, in this case, no, we'll do just marker. Okay. Is a collection of edges that covers all of the edges, all of the vertices, sorry. So for example, this might be a spanning tree, and it's spanning because it covers all the vertices, but it's a tree because it has no cycles. So the tree part of this is no cycles, and the spanning part is covers all vertices where I'm assuming that either my graph that I begin with is connected to begin with, or if I'm using a graph that is not connected, then I have to divide it into connected components, and then I add all of the possible spanning trees for each component. So it would be a spanning forest in the case of a graph that's not connected. In the transversal case, rank is a little bit less straightforward. So I may leave it out. So in the transversal, rank actually connects to I'm going to call it routings, but I'm put an asterisk because I may not come back to it, just to keep moving. So it connects to something, but this one is not as immediate. So now we have an established definition of independent sets, and then how to generate them, maybe from a smaller collection like the basis. What we haven't mentioned yet is, you know how in topology you do the definition based on the open sets, but you can also do it based on the closed sets. We could do the definition here in terms of the dependent sets. So the analog for all of the independent sets would be something like a script D of all of the dependent sets, maybe not equal to, but some kind of analog. And if I had a basis, then an analog here is going to be all dependent sets. And then this one here is going to be circuits, which means that I now need to define circuits. So, definition. A circuit is going to do the job of being a cycle. So the things that I was avoiding before. Matroid is a minimal dependent subset of E. So before, for a basis, I was looking for maximal independent, and now I'm looking for minimal dependent. And there is a system of axioms to go with this. C2, C3. First thing, this should not be a circuit. Second thing, if I have a circuit, then no proper subset of it is also a circuit. So essentially, if this was a circuit and I remove one edge, then that's no longer a circuit. So proper subset of this one, D is not in my collection of circuits. And then the third one is I can join circuits. So if I have one circuit here and it shares an edge with another circuit over there, so I have C here, D there, I can create a new circuit that should also be included in my collection by just joining through the common edge. So if I have two circuits here with a common edge, so there is some larger circuit that contains them. Actually, not this, let me just say with somewhere. Fine, okay. So E contains, I'm going to put it informally, C and D. So it's the picture ID, or I can merge the circuits to make a larger one. New system of axioms. So this should go with the proposition or theorem, if you will. That says, if I just give you a set E, a ground set E, and then a collection C that satisfies these properties, I can always recover a matroid. If I had these two things, C1 through C3, describes a matroid. So I can again recover the information about independent sets, because I can recover, where did I write? I didn't write it here, fine. So we cover independent sets from circuits. Main idea. I don't have the formula in my notes, and I don't want to go back to the other ones. So I'm going to introduce a couple more axiom systems later on, but just to make a point about the axiom systems, they're not supposed to be used one at a time if you're trying to prove that something is or isn't a matroid. They can be used together, so to speak. So that you might have a result that looks like it should be about bases, but you actually prove it through circuits. Or you have something that looks like it should be about the independent sets directly, but you prove it through a different set of axioms, because they're going to be all equivalent. The idea is that you can always recover a matroid from them. And in particular, that's used in this theorem where you introduce dual. So you can define the dual of a matroid. How am I doing in time? So if I have a matroid defined in terms of ground set and its basis, I can define the dual basis as just the complements. This is called the dual basis, and proposition. In fact, that same ground set with this new basis is also a matroid. So we call this the dual matroid. Meaning if I had M being E, B, then the dual is E with this B star. And this proof, though it looks like it should be in terms of the basis, is actually done through circuits. So that was just as an example, and also quick introduction to a possible construction of matroids through existing things. Questions or? It's just really quiet, so I can't tell if I'm talking to myself anymore.
You're still doing good. Not yet. I'm curious.
Okay.
Well, keep going. I'll ask in a second.
All right. So as long as duality is allowed, let's say, if you're following so far with the duality, duality is useful because I can tie it back to the notions of duality that we already know from before. So right now it's acting like a set complement, which fine, whatever. But duality has meaning depending on the context. So in linear matroids, duality is either orthogonality, where it exists. Like whenever you have a space where orthogonality makes sense, then you use that, but also just a regular duality that we know and love from before. And in the case of graphic matroids, then you relate it to the graph dual. So dual graph where the dual of a graph, suppose that I had something like this. This is G. To create the dual graph G star, what I'm going to do is for each of the faces, so each of the bounded or unbounded regions in this picture on the left, so I have one bounded region here, one bounded region there, and then one region outside. I'm going to have those as vertices. So the vertices are faces or regions. And my edges are going to be whenever two regions are neighboring regions, I can connect them with an edge. So these two can be connected. These two can be connected. And basically every time I cross an edge to go from one to the other, technically this is part of the same region that connects this way to that edge. And no, that's it. So what am I missing? This. Am I missing any more regions? Oh no, yeah, I do need these. Okay. There we go.
What do
So
you do if
connect.
the graph is not planar?
Sorry?
What do you do if the graph is not planar? Because this seems to only work if, I think.
Correct. So there's actually a subcategory of graphic matroids where you're only looking at the planar ones. And what's going to happen is that the planar graphs play nice. If the graph is not planar, then a lot of properties are not actually preserved. So you can prove that the dual of a linear matroid is also linear, but the dual of the graphic matroid is not necessarily graphic. And that's going to depend on whether or not the graph is planar.
Okay.
So it's a cute property to have, but yes, you're right, it depends. And then the other thing that it depends on, or actually no, the thing it doesn't depend on, though it looks like it might be, is, so let's just make this note. So different embeddings of a graph G may have different duals. The dual matroid is unique. So the example here is, it shouldn't be too hard to believe me if I say that this graph and this graph are embeddings of the same thing. This is one embedding. This is another embedding. But if I do the dual for both of them, I'm going to get different dual graphs. So these go to a G1 star and a G2 star that are not in fact isomorphic. However, if I do the matroids oh, same thing, but let me just, for the sake of uniformity, put this there. The matrix will be the same. And this is equal to if I put the star inside. So even though these two are not isomorphic as graphs, the matroids do preserve that structure. So that's dual matroid is unique. Trying to figure out how much more to jump through. So yeah, maybe I'm just going to do a quick summary of the next few things I wanted to mention. So we'll do it here. There exists more axiomatic definitions for matroids. So far I gave axiomatic definitions in terms of the independent sets, in terms of the basis, in terms of circuits. These are in terms of a rank function. So rank is a function that goes from these to the natural numbers. And I can also have one in terms of a closure operator. And that's going to be from subsets to subsets. There we go. So I'm going to skip over them because we don't have time. There's only like 10 minutes left. And instead, maybe I'm just going to point out some results in picture form. Because I've been talking about nice types of matroids. I've mentioned linear, I mentioned graphic, I mentioned, let's say, inspiration for them, where you might encounter them. But the big one is the abstract matroid in terms of just E and I. So matroids, the big set is, or the big collection, the big class is here. And inside them we have algebraic matroids. Inside of that we have linear matroids, and then we have graphic and transversal, which only sometimes overlap. Of course, each of these containments and the overlaps are theorems, and they're proved sometimes algorithmically. Like you just have an algorithm that checks whether or not something will turn into a matroid. But just to kind of tie in together some of the things that we've mentioned so far. Let me see what else might be worth mentioning.
Sorry, am I understanding correct? Sorry, am I understanding correctly?
Yeah.
Correctly, the diagram that every matroid can be seen as an algebraic matroid?
No. So
okay. So there is another circle around algebraic.
Correct. So there are things out here that are not algebraic. So maybe
On another circle then.
yeah, so this algebraic refers to whatever's inside this bubble. Yeah.
Okay, fine,
So
I understand.
yeah.
Sorry, I was surprised
No,
otherwise.
you're
If
fine.
every matroid was algebraic, it would have been very cool.
No, then what am I saying is to call them algebraic, right?
Okay.
So the linear
Okay.
ones are here. Yeah, which
Thank
is
you
true.
very much. Sorry.
Yeah. Transversal is referring to this. There we go. And then the big matroid set is this one. Let's see. Maybe I'll just do a quick one because it's an application that would maybe relate to the example we saw. So related to example 3, a task would be, Dr. Sapchik, Dr. Rimby, whoever's doing the CA assignments is interested in finding algorithmically a quick solution to how do I give each TA a job. And in the topic of algorithms, we could be looking at graphs like this. Let's pretend now that we are government officials and we're trying to connect cities, but not all of the roads have the same costs. And we would ideally like to have all of the cities connected somehow, even if we don't care how long it takes any person to go from one point to another. So I may not want to actually build all of the roads, but they might have different costs associated to them. A solution strategy when you're trying to choose which roads to build. Oh, I need another weight for this one. We'll put a weight 2 here. A solution strategy would be, if you're very lazy, you just pick the cheapest road or one of the cheapest possible roads and you build that one first and then hope for the best. So I could choose to build this road. And then I could choose to build this road because it's still the cheapest one and I can use it. The one thing I don't want to do is, for example, choose this road next, or even if it were, price 2 or price 1, because there's no point in making a cycle. If all I need to do is connect this point to that one, it's enough to connect it via this other. I don't need the shortest path. I just need the cheapest overall spanning tree. Then I can choose one of the two ones. So for example, I could go here. Then I check again. I don't want to do this edge because that would close a cycle. I don't really want to do a cycle, but there's another one that's also cheap here. Then I can look at the edges with price 3. There's only these two, but I'm going to ignore the one that closes a cycle. Oh, and cover this one instead. So I'm going to build that road instead. And now all I'm missing is the city that's over here. So regardless of the fact that the other roads are cheaper, I'm just going to finish by building this road. That strategy of at each step building the cheapest road at each step is called a greedy algorithm. And you would, of course, use it to solve this kind of problem, right? You tell a computer to just successively run these steps. Maybe it won't always find the same path because at some point you have choices that you can create multiple solutions. But the takeaway here is that in Matroids, the greedy algorithm works. In fact, they are the only simplicial complexes where it works, where it does. Now, I'm throwing a curveball and mentioning simplicial complexes, but this is related to the fact that if I just look at the 3 axioms, I1, I2, I3, these first 2 axioms alone would describe an abstract simplicial complex. Because all I need for an abstract simplicial complex is that all of the subsets of a simplex are also simplices, and that's the containment. And then the empty set is a simplex, so that includes the first axiom. So what I'm saying with this statement is that the fact that the greedy algorithm works is interchangeable with axiom 3. So you can characterize Matroids in terms of the kinds of problems you can solve with them. And that was just one quick application to close out so that it looks like there's a point to studying them in terms of solving problems with them. And I think that's time for me. So if anyone wants to ask questions, stick around for a little bit.
Well, eventually I'll find a better way to do that.
I do have a question, which is either very difficult or very stupid. So
We'll
let
see.
me
I have
ask.
a lot of notes that I didn't get to write down, so maybe it's just something I forgot to write down.
No. So there is a principle on the that is called the projective plane duality. I mean, it's something that allows you essentially to convert statements on the projective space if you switch the dimension. So, for example, if you have like through 2 points, there is exactly 1 line. This is the same statement as between two lines always intersecting 1 point in the projective space. These are actually exactly the same statement, one in the space, one in the other one in the dual. So if one is true, the other one has to be true because the dual spaces are kind of isomorphic. Do you have this kind of duality also in the Matroid case or not?
Yes.
Okay.
But I think it's going to be more a duality between what it means in terms of matroids and what it means in terms of a particular kind of matroid. So for example, when I was building these parallels between what orthogonality means in one case versus in the other, let me see where I have the orthogonal. Where do I have the duals? Here. So there's like an entire section that I just skipped over. But this orthogonality, you can use it to relate matroids. So the result, let me just throw in a page here.
Mhm.
Oh, hold on. That freaks out if I forget. No, I just want the, here, okay. I know I just shift the text when I add a new page, but anyway. A result is the dual of a transversal matroid
Mhm.
is called a cotransversal matroid. And I already mentioned that transversal matroids are linear. So this corresponds to some linear subspace, right? As it turns out, if this corresponds to some V as a subspace, this corresponds to some V orthogonal. So you can, go back and forth between orthogonal properties and the vector space and the dual properties and the matroid sense. I don't know if it's
Okay.
exactly what you mean in terms of
Yes, yes. That is in this philosophy, of course. Yes. That's interesting. Thank you.
Any other questions? I have one, but I'm gonna wait maybe. Okay, so maybe I'll ask my question then. Could you go back? I think it was the diagram you had with the square and the types of matroids.
Oh, so the big one.
Yeah, that one. So I think the first question I had is whether or not just the fact that you drew this big box probably tells me the answer is no. But is classification of all matroids some sort of object that you can say it's a matroid of this type, and every matroid is a matroid of that type, like Giacomo was saying earlier, like they're not all algebraic, but is there some structure, I guess, that you can
What
say?
do you mean the structure?
So I mean, like some underlying. So you can say that there's a graph associated to this matroid.
Oh yeah. So there are
it,
constructions for these things, if that's what you're asking.
yeah. So
And there are theorems, and they go to like it took them a hot minute to come up with them. For a while, people thought that all the matrices were algebraic, and then they found the counter examples. The same with like linear, graphic, transversal. Sometimes you don't actually have to check everything. You just have to check clever things.
yeah.
I'm trying to remember. I can give you the reference for the one that lives here, but I don't have it on my notes.
Okay. Is it like a known kind of? What was the? Do you know what the object was, or not really? Or is it just
No,
like
not really. I just remember it was like a theorem, so it's a named thing. But I can't remember the actual structure. One of the, let's say, counterexample ones was the Fano matroid. So you can play around with an equivalent of the Fano plane. So it's the, and then it has, wait, maybe I can do this and make it, of course not. When I'm trying to draw anything else, there we go. And then these are, nope, let's draw, okay. Pretend that these lines are straight and that, you know, the triangle meets where it's supposed to. Do I have all, should be 7 things. And so this is the final plane. But this is connected to hypergraphs. So in this case, each of the edges is a 3 set instead of a 2 set. Associated to this, there is a Fano matroid. And it's the only counterexample that I remember that comes out, you know, off the top of my head, but it's not a counterexample to the non-algebraic thing. It's a counterexample to something else.
Sure,
but usually with a counterexamples, what you're looking for is that they don't contain particular substructures. Like there are theorems that say a matroid is algebraic if it does not include these things, or it is, and there are specific lists of what to look for. Like, you know how with planar graphs you say it cannot have a copy of K5. Like, you know, no graph that has this can be planar. No graph that has K33 can be planar. There's equivalent statements for matroids, like they cannot contain certain things, and then you rule them out of the categories.
Okay. That kind of answers.
So I know that's a strategy for some. Yeah, but I can't, like off the top of my head, I can't name them for you. I just know that it's somewhere buried in what I was looking at. but I didn't include it here.
Perfect. Cool. So, any other questions from anyone else? If not, let's thank the speaker one more time, and we can just stop, I guess.
Thank
Okay.
you.
It looks like for me, but I don't know. See Brittany.
Yep, it's me. What up? Anna's leaving.
Oh, no, she's still here.
Wait, is she here? I thought she was on
Yeah.
the plane already.
I am in New York, but I can.
Oh, are you at
So-
JFK?
Yeah, wait. I can show you my face. It's funny.
Wow.
But I cannot. I am from my phone. I don't know how
Ah,
to kind
I
of.
see. We see you.
look all of you.
Oh, I
We
see.
you. We see you.
Maybe you tap it and it'll give the little switchy thingy.
Yeah, you
Yeah,
You know?
because I want to see you all together, but I don't know how to do it from my phone.
There's two things in your fridge. There was like 10 things left. There was like 2 gallons of water.
Okay, like this. I see how to do it. Okay, good.
Yeah.
Yeah, here I
You did it?
am. So I am with my N95 mask. So and at 5 p.m. I will leave for Rome. Very excited.
Okay. Yay.
Lina, I could do your seminar like at 3:30 or 2:30. Sorry, 2:40 actually. Yeah. But I saw that you recorded it. Actually, we are still recording